Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 10 on Symmetry. This is our last lesson in Unit 2, which has been all about transformations and where we've concentrated on rigid motions, right? Those are transformations that preserve both length and angle measurement, which means they preserve the shape and the size of a particular figure. Now today we'll be talking about symmetry, which are very special types of rigid motions. Let's get right into it and figure out what the definition of symmetry is. All rigid motions map a figure to an image that is congruent to the original figure. In fact, that's now how we're going to technically define congruency. There are special types of rigid motions known as symmetries that do even more than that. So let's bring it up and talk about what a symmetry is. Symmetries of figures. A transformation that maps or carries a figure onto itself is known as a symmetry of that figure. Exercise number 1, explain why a symmetry of a figure must also be a rigid motion. All right, well, before we kind of get into exercise number 1, all right, which should be pretty easy, I just really want you to understand what a symmetry of a figure is. You've been talking about symmetry for a while. All right, you've probably talked about symmetry as early as maybe even 4th grade math, where maybe you drew in kind of a line and said, this figure is symmetric across this line or something like that. And that definitely has something to do with symmetry. We'll see lines of symmetry in just a bit. But symmetries are more explicit than that, right? They are literally transformations that after you've done them to the figure, the picture, the image that you get, looks exactly like the original figure, not only in shape and size, but literally exactly in the same location, in the same orientation. So for instance, here we've got the hypercube, the eMath Instruction logo, the eMath Instruction hypercube. Now, if I take this hypercube and I start to rotate it around its center point, right, eventually what happens is it ends up rotating enough that it ends up falling on itself. It gets mapped onto itself, all right? And then I could even rotate it a little bit more, right? And eventually it gets mapped onto itself, right? At least I'm gonna try to map it onto itself. Those two rotations around the, quote, center of the hypercube would be considered symmetries of this particular hypercube, because after I've actually done that to the hypercube, the image that I'm looking at looks exactly like the original pre-image, not only in shape and size, but also where it's at. And that's what it means to map a figure onto itself, meaning that every point that I sort of do the transformation on lands on a point from the pre-image. So now let's go back to the question in exercise number 1, which is to explain why a symmetry of a figure must also be a rigid motion. Pause the video now and see if you can explain that. Well, it's pretty simple. In order to map a figure onto itself, right, the image must be congruent to the pre-image. Right? And if the image is congruent to the pre-image, then whatever was done to it must have been a rigid motion, right? I mean, obviously, if for some reason we do a transformation and it changes the size or the shape of the object of the pre-image, then there's no way it could map onto itself, right? So, in order to map onto itself, the image must be congruent to the pre-image, so the transformation must be a rigid motion. Great. That's it. Even with my messy handwriting. In order to map onto itself, the image must be congruent to the pre-image, right? Whatever this thing was, Whoops. Oh, there it is. There's my little rotate, right? Here I'm rotating, I'm rotating, I'm rotating. Now that didn't map onto itself, but clearly oh, that's so cool looking. But clearly the image, right, was congruent to the original. But then, once it maps onto itself, right, that final image, after I just did that rotating, must have been congruent to the original image. Otherwise, I would have seen other stuff. It wouldn't lie on top of itself. Okay, now that we've got that straight, let's keep talking. Exercise number 2. In the figure shown, triangle ABC is isosceles with side or segment AB congruent to segment BC as shown. Letter A. Describe a reflective line of symmetry for this figure. Draw it to the best of your ability. Lines of symmetry are often drawn dashed to distinguish them from the actual figure. All right. Well, you've probably done this before, but what I'd like you to do is try to draw a line up on that figure. You can use a ruler if you want, or you can just sort of hand sketch it, right? I'd like you to sketch it in dashed, where if you took this figure and you reflected it across that line, it would map onto itself. Go ahead and do that. All right, well, it's simple enough, right? And we sort of looked at this line on the day that we spent talking about isosceles triangles. The line that we should be drawing is that angle bisector of the vertex angle, or you could also say the altitude from the vertex to the base. So I'm going to actually do it using the ruler. I'm not really exactly sure why, but let me just bring it up here so that we've got a nice line of reflection. Again, since it's a line, I'm going to actually extend it a little bit past that. All right, and we get our line of reflection, okay? And I want to describe it, right? So I could say that it's, let's say, a line drawn through B. Man, the red's coming out today. A line drawn through B, perpendicular to segment AC, right? So it's that particular line. All right, and we know that that's a line of symmetry. We've talked about this on the day with the isosceles triangles, right? If I reflect that figure across that line, C is going to map to A, and of course B is going to map to itself because it lies on the line of symmetry. All right, let's take a look at letter B. Does the figure have rotational symmetry? So, you know, in previous courses, when you've worked with symmetry, you've almost always just worked with lines of reflective symmetry, or lines of symmetry, as they're called, okay? But there's two major types of symmetry: lines of symmetry and rotational symmetry, or reflective symmetry and rotational symmetry. Rotational symmetry occurs when we take the object and we rotate it around some random point by a certain amount and it gets mapped onto itself. And again, we saw that repeatedly when we were looking at our hypercube, right? That thing has beautiful rotational symmetry. It also has a lot of lines of reflective symmetry, but again, we're not going to analyze those right now. So the question then becomes, back on this slide, does this thing have rotational symmetry? Think about that for a minute, and then let's play around with it. And the answer is, for a general isosceles triangle that isn't also an equilateral triangle, the answer is no. All right? And again, it's pretty easy to see that if I come in here and click on this thing, and I start to rotate it, right? What I'll see is that no matter how much I rotate it, unless I rotate it an entire 360 degrees, which really doesn't count, right? Then there is no angle of rotation that is going to make it end up fall on itself. Okay, so the answer is no. All right, let's keep going. Now let's talk about regular polygons. For the rest of this lesson, we're going to concentrate on the symmetries of regular polygons. So first, we should understand what regular polygons are, and then we'll analyze them. Regular polygons. A polygon whose sides are all equal length and whose angles all have equal degree measures. All right, so this is cool. You can take any shape, with however many sides you want. I'm sorry, any polygonal shape. So a shape that's got straight sides, right? And you can basically make one that is a regular polygon where all the sides have the same length and all the angles have the same measurements. Now let's talk about that in the case of a triangle. Exercise number 3. The simplest regular polygon is an equilateral triangle. Equilateral triangle EFG is shown below with one line of symmetry drawn. Letter A, using a straight edge, do your best to draw the other 2 lines of symmetry. Mark their intersection point as H. We will call this the center of triangle EFG. All right, well, why don't you go ahead and do that? Due to the symmetry of this particular triangle, i.e. that side, and that side are all the same length, the other 2 lines of symmetry should be rather obvious, but why don't you go ahead and sketch them in? All right, well, for me, I had my sort of graphics do it for me. All right, so there are our 3 lines of symmetry, and each one of them is similar to that line of symmetry we saw with the isosceles triangle, i.e. the line of symmetry starts at the vertex and then runs perpendicular to the opposite side. Starts at a vertex, runs perpendicular to the opposite side, and perpendicular to the opposite side. In fact, each one of these lines of symmetry is, not surprisingly, the perpendicular bisector of that opposite side. It has to be, because if it's not, when you flip it across that line, then, if this thing, let's say this dashed line, wasn't the perpendicular bisector of FG, then when I reflect across that line, F wouldn't map to G and G wouldn't map to F. So it's got to be that perpendicular bisector. All right, that being said, now letter B, give all angles of rotation about point H that would map triangle EFG onto, it should say onto itself, but it actually got covered up by the graphic there. I apologize for that. So it should say onto itself. All right, so let's play around with this for a little bit. And I want you to really understand this. So I'm going to bring my compass up just for a moment. All right, I'm going to make it larger. Whoops, I'm going to try to make it larger. All right, and then I'm going to rotate it kind of like this. Okay? Now, the idea is I could certainly rotate this blue triangle. Okay, and I will eventually rotate the blue triangle. Oops, I just want to make this a bit smaller. There we go. All right, but what I'm going to do is I'm going to actually take this little compass mark here, and I'm going to rotate it down as if point F was rotating around to match up with point G. All right, so let's pretend that's point F, and it rotates all the way down to point E. All right, great. Now, what angle was that? One of the cool things is my compass will actually allow me to put it out there, and it's a little bit wrong because I've rotated it a little bit too far. Let me see if I can actually get rid of that. Nothing like trying to make a point that then is not made. Come on. Delete, delete, delete. It's not doing it. Oh, why is it not doing it? I'm going to delete that. There it goes. Okay, let me see if I can get it correct. There it is. All right. So I had to rotate it 120 degrees. All right, let's actually see how that rotation is done with the actual triangle. Right? If I click on my blue triangle and I rotate it, right, that will rotate 120 degrees. And specifically that 120 degrees is that angle, right? And you can see it, right? It's right there, right? That 120 degree angle. And then, of course, if I rotated it another 120 degrees, it would land right there. So that would be another 120 degree angle. And of course, that would give me a total rotation of 240 degrees. The final rotation of 120 degrees, well, that would just simply then be a 360 degree rotation, which is a symmetry of every figure. So sometimes it's listed, sometimes it's not listed. But let's do it. So we've got a 120 degree rotation, a 240 degree rotation, and might as well throw it down a 360 degree rotation. All right. Now, why is it 120, 240, and 360? Or better yet, why is the smallest one 120? Well, if you think about it, right, and we just look, let me change colors here so that we can really see this beautiful contrast. If we just simply look at this, so forget about the overall triangle, just look at this kind of figure in red, right? What we should know is that if we go all the way around these angles, they must sum to 360 degrees. Now, the ones that I care about, which are these angles, this angle, and this angle, right? I can figure out what that angle is by simply doing, wow, that's interesting. I didn't realize those were all separate elements. I can, doesn't want to delete. I can figure out what all of those are by simply doing 360 divided by 3 and get 120 degrees, right? So that's why that minimum angle is 120 degrees, because really from the center point to any vertex, what I'm going to get is these three, if you will, they're almost like radii, right? They're almost like the radii of a circle that goes all the way around that equilateral triangle, right? And so I can figure out those rotational angles of symmetry that way. Let's take a look at our next figure. Not surprisingly, when we go up from the equilateral triangle, we then get a four-sided regular polygon, and let's take a look at what's going on with that. Exercise number 4. A four-sided regular polygon is one of the first shapes you ever learn, the square. Square LMNP is shown drawn below. Letter A. Two of the lines of symmetry for the square are drawn with their intersection points marked as Q. The square has two additional lines of symmetry. Draw them. All right, go ahead and draw what you think are the two additional lines of symmetry. I bet you can figure these out. All right, now this is a little bit different than before, all right? Before, my lines of symmetry were always just going from a vertex perpendicular to the other side, but now I'm gonna have also a line of symmetry like that, and a line of symmetry like that, right? So now, right, keep in mind with the equilateral triangle that I just saw, I had three different lines of symmetry. With the square, I have 1, 2, 3, 4 lines of symmetry. Hopefully you're seeing just a little bit of a pattern there, right? Let's take a look at exercise B. What is the minimum angle of rotation about point Q that would map the square onto itself, illustrate on the image? Right? So what do you think is the minimum amount that I would rotate the square around point Q? And again, the real question then becomes, what would it take to map point M onto point L onto point P onto point N, etc. Think about that for a moment and see if you can come up with an answer. Well, if you said 90 degrees, well done, right? Because the plain fact is this angle, right, which is the angle that I'm looking for, is the same as this angle, which is the same as this angle, and the same as that angle. And I can figure those out by taking that full 360 degrees, dividing it by 4, and I get 90 degrees, right? So that's a 90-degree angle, a 90-degree angle, etc. All right? Now, real important though, besides the 90-degree angle, we have two other angles besides that 360 that will also map the square onto itself. What are the other two angles? Pause the video now. Well, if you think about it, what would it take to map point M to point P? Well, it would take one 90-degree rotation, another 90-degree rotation for a full 180-degree rotation. Right? So I would have a 180-degree rotation. Then I could do, what would it take to map point M all the way to point N? That would be a 90-degree plus 90-degree plus 90-degree, or 3 times 90, which would be a 270-degree rotation. If I did it 4 times, then of course I'd get 4 times 90, which would then be 360 degrees. Now, I haven't been talking about clockwise or counterclockwise, and maybe I should, but because these are regular polygons, it doesn't really matter whether you're rotating clockwise or counterclockwise. Those angles of rotation will still be, in this case, for a square, 90, 180, and 270. And then the full 360, but again, that's true of any figure. Okay, we keep moving on up, right? So we did a 3-sided regular polygon, a 4-sided regular polygon, and now we move up to a 5-sided regular polygon, also known as a pentagon. Let's take a look at exercise number 5. A 5-sided polygon is known as a pentagon. Regular pentagon A, B, C, D, E is shown below with one line of symmetry already drawn. Letter A. All other lines of symmetry are like the one drawn. Sketch them in by hand. Mark their common intersection point as point F. All right, why don't you go ahead and sketch all other lines of symmetry in by hand. All right, here we go. Well, we're back to the idea that we have a line of symmetry that goes from the vertex of one of the points on the figure perpendicular to the other side. So I could do that also with point A. I could do a line of symmetry like that. Point E, I could do a line of symmetry like that. Point D, I could do a line of symmetry like that. And point E, that is gorgeous. I could do a line of symmetry like that. All right, great. So again, not surprisingly, right? 1 line of symmetry, 2 lines of symmetry, 3, 4, 5, right? There's a line of symmetry for each vertex. So there are 5 lines of symmetry, not surprisingly, for a 5-sided figure. All right, let's take a look at letter B. What is the minimum angle of rotation about point F that will map A, B, C, D, E onto itself? Illustrate on the diagram. Awesome. Well, why don't you go ahead and do this, and then we will talk about it. Okay, and again, the idea here is, let me go into red so that it contrasts nicely with the blue, right? What would I have to do to map point D onto point C, and likewise point C onto point B, and point B onto point A, etc.? Well, we've got these, right, sort of radii going out from that center point to the vertices. So all I have to do is do 360 degrees by 5, divided by 5. Of course, that's convenient if you've got your calculator out to just do it there. If you already know it, great. That ends up being 72 degrees. So the minimum angle of rotation in order to map this figure onto itself is 72 degrees. If I wanted to figure out all the other angles of rotation, I would simply do 2 times 72, which would be 144, 3 times 72, which would be 216, etc., etc. All right? And of course, there would be a bunch of different angles, 5 angles in total if you count the 360-degree angle. All right, let's take a look at letter C. What counterclockwise angle of rotation about point F would map point C onto point E? All right, see if you can figure out this. Okay, well, I want to take point C, I want to rotate it counterclockwise so that it ends up at point E, right? Counterclockwise so that it ends up at point E. Well, in order to do that, I have to rotate it 72, another 72, and another 72, right? So I've got to do 3 times 72 degrees, and that is 216 degrees, which is one of the various angles of rotational symmetry. Okay. Now, a pattern for regular polygon symmetries. From our last few examples, patterns should be emerging concerning both the lines of symmetry and the angles of rotational symmetry for regular polygons. So let's see if we can extend that now and figure out some of the symmetries of these other regular polygons. Exercise number 6. A regular hexagon, 6 sides, octagon, 8 sides, and nonagon, one of my favorite words, 9 sides, are shown. Sketch all lines of symmetry and give the minimum angle of rotation about the center point that would map the figure onto itself. All right, now one thing about lines of symmetry is it really depends on whether the regular polygon has an even number of sides or an odd number of sides. So for instance, the hexagon, right, 6 sides, has an even number of sides, which means that all of the lines of symmetry, let me go back to blue, all of the lines of symmetry are going to simply be the perpendicular bisectors of these sides, right? You're going to sort of connect a side to a side, and then a vertex to a vertex. Right, so this is more similar to what we had with the square, the 4-sided figure. Right? Every one of those lines is then going to be a reflective line of symmetry. On the other hand, let's skip over the octagon for a second. A nonagon with 9 sides, right? Its lines of symmetry are going to go from a vertex, that was interesting, are going to go from a vertex perpendicular to the opposite side. So in that case, what happens is you just kind of want to start with each vertex and just draw a line perpendicular to the opposite side. But one thing is definitely true. It will have the same number of lines of symmetry as it does sides. So the hexagon should have 6 lines of symmetry, the octagon 8 lines, the nonagon 9 lines, and be careful. Don't count the ends of the lines, because if you do, you'll think this thing has 12 lines of symmetry, and it doesn't, right? That's an entire line, that's an entire line, etc. So see if you can draw in those lines of symmetry, and then let's talk about the minimum angles of rotation. Okay, so here we go. For the octagon, it's going to be pretty similar to the hexagon and to the square. It's going to get very busy very quickly. I just don't want to miss any. That was terrible, that last one. All right, hopefully we can do a little bit of a better one here. We'll see. Man, I wish I was just doing this on a piece of paper. I think that last one looks a little bit, oh, I think I missed one. Yeah, I did. Yeah. Actually, I missed a couple. Jeez. That's what happens when you have a 9-sided figure. Yeah, that kind of looks like an alien. All right, awesome. I should definitely do this with a ruler in the future. Okay, or just not have a 9-sided figure. That looks just horrible. Let's talk about the minimum angle of rotation. All right, now the minimum angle of rotation is quite simple. Right? You just have to think about what you have to do to rotate one vertex so that it gets to the next vertex, right? But the key there, right, is that you simply need to look at the number of vertices, right? In a hexagon there are 6, and you need to divide 360 degrees by that 6. So the minimum angle of rotation for a hexagon, a regular hexagon, is 60 degrees. Why don't you go ahead and figure out the minimum angle of rotation for an octagon and a nonagon? Man, those lines of symmetry. They are just poorly drawn. I think the hexagon's not too bad, but all right, for an octagon, it's going to be 360 degrees divided by 8. That's 45 degrees. And for a nonagon, it's going to be 360 degrees divided by 9, and that's going to be 40 degrees. You can then, if you need to, get every other angle of rotation by just multiplying these by whole numbers. So for a hexagon, we have 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300 degrees, and 360 degrees. I won't go through them all for these, but all you have to do is multiply 45 by 2, by 3, by 4, by 5, by 6, by 7, by 8, right? And it's beautiful, right? One of the reasons that we like figures like these is because of the symmetry that they have, right? The reason that you'll see regular hexagons in lots of different designs, right, is because of the symmetry that they have. In fact, if we go all the way back to the first slide, or the second slide, I guess, right? One of the reasons that I find the hypercube so amazingly sort of like interesting to look at is because it's based on an octagon and has all the different symmetries of the octagon, right? Not just those rotational symmetries, but it also has those reflective symmetries, right? If I were to reflect the octagon over any of those lines, including other ones that I haven't drawn, it would get mapped onto itself. For whatever reason, human beings like symmetry in figures. They like to be able to sort of look at a figure and see, oh, if I rotate that by a certain amount, it'll land on itself, or if I reflect it over itself, it'll land on itself. If you've ever seen the art of M.C. Escher, right? Some of that can be like very weird looking, but a lot of it is very appealing because of all the symmetry that occurs in it. I actually encourage students after this lesson to, whenever they're out sort of in the real world, as opposed to the math classroom, which apparently is not the real world, right? Look for things that have symmetry. Look for objects, designs, artwork, anything where you can say, oh yeah, if I drew that line in and I flipped this thing across that line, it would get mapped onto itself. Or if I took it and I rotated it by a certain amount, it would fall upon itself. Oftentimes you'll see objects with 180-degree rotational symmetry as their only symmetry. You can rotate it a half turn and it will land on itself. Symmetry is one of the most fascinating and interesting ideas in all of geometry, and there are certainly many college-level math classes that you can take which studies it a lot deeper. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.